Before the infinite reaches of space, where galaxies clash and stars are born, is a mystery deeper than anything humanity has ever faced. This is an enigma that pushes the boundaries of reality, defies the rules of physics, and has the potential to destroy the foundations of existence itself. Even though they remain hidden and unnoticed, their influence is impossible to ignore. They are the force behind the universe's expansion, they hold galaxies together, and they defy understanding. Could dark matter and dark energy hold the key to unlocking the ultimate secrets of the universe? Do the answers we seek challenge everything we think we know? Are you ready to dive into the secrets of the cosmos? Join us as we embark on a quest to unravel the secrets of dark matter and dark energy, and to confront the mysteries that lie on the edge of our understanding. 100 years ago, astronomer Edwin Hubble made two astounding discoveries that laid the groundwork for modern cosmology. First, that galaxies do exist, but they are incredibly distant from us. Second, that these galaxies are actually moving away from us. That is to say, he found out that the cosmos is enormous and is growing much larger. The Big Bang Theory, which holds that our universe was once smaller, hotter, and denser than it is now, is the foundation of modern cosmology. This very basic assertion is supported by a wealth of data, yet it does not indicate that we fully comprehend the workings of the cosmos. There are in fact two stark gaps in our knowledge. One of these was identified in the 1970s and is known as dark matter. To the best of our knowledge, dark matter is composed of a novel type of particle whose identification and characteristics remain unknown. Although it makes up the great bulk of the universe's mass, dark matter is completely unrelated to light and ordinary matter. Dark matter has eluded direct observation by scientists thus far. It is undetectable by present-day instrumentation because it does not interact with baryonic matter and is entirely opaque to light and other types of electromagnetic radiation. The gravitational impact it seems to have on galaxies and galaxy clusters, however, has scientists certain of its existence. For example, the visible substance of a galaxy is concentrated towards its center. Therefore, stars there should travel considerably more slowly than stars on the outside, according to conventional physics. However, data from space reveal that stars' orbital velocities are rather constant across the galactic disk. This mysterious outcome can be explained if the boundary stars are subject to the gravitational pull of an invisible mass, dark matter, located in a halo surrounding the galaxy. Some of the deep universe optical illusions that astronomers have observed may also have a dark matter explanation. One possible explanation for images of galaxies with unusual light patterns, like arcs and rings, is gravitational lensing, a process wherein large, unseen clouds of dark matter distort and magnify the light from even further away galaxies. Dark matter is an elusive concept. However, scientists have a few theories. A popular theory holds that exotic particles that do not interact with ordinary matter or light, but yet produce a gravitational pull, are what make up dark matter. Several scientific teams are presently engaged in the process of creating artificial dark matter particles for laboratory research. One of these teams is based at CERN's Large Hadron Collider. However, many believe that a fundamental shift in our understanding of gravity might account for the observed effects of dark matter. These theories propose that our familiar sense of gravity is different from the large-scale gravity that controls galaxies, and that there are different kinds of gravity altogether. According to the most widely accepted dark matter model, cold dark matter, or CDM, dominates the universe gravitationally, with stars, planets, and living things making up a very minuscule percentage of the universe's mass. According to the cold dark matter theory, smaller things first collide due to gravity before merging to form larger, more massive objects. Because they originated in the early universe and are currently utilized to produce larger structures, dwarf galaxies are an excellent example. The cosmological large-scale structure of the universe is mostly consistent with this idea. The cold dark matter theory is the idea that most cosmologists believe best explains how the universe came to be and how galaxies and their clusters are part of its large-scale structure today. It is thought that cold dark matter is made up of particles of some kind with invisible properties. These particles have been proposed as either sterile neutrinos, massive compact halo objects, machos, or weakly interacting massive particles known as WIMPs. WIMPs are considered to be the most promising option for dark matter composition. The existence of WIMPs in nature is still speculative though. There are a lot of different experiments that are trying to determine whether or not sterile neutrinos are a part of dark matter right now. Although large-scale structures are formed by dark matter, there appears to be an enigmatic process tearing them apart, as scientists have seen. This unexplained quality of force, sometimes called dark energy, is speeding up the expansion of the universe. Its name is a little misleading, like dark matter, since it is more invisible than dark, because it does not interact with electromagnetic radiation. Its nature necessitates explanations that are highly theoretical and involve concepts that might be controversial. It initially showed up as the cosmological constant in Albert Einstein's field equations for general relativity. To accommodate a static universe, he suggested modifying his equations in this way. But American astronomer Edwin Hubble found in 1929 that galaxies outside of the 10 megaparsec or 33 million light-years range were accelerating and shifting their emitted light to the redder end of the visible light spectrum. It was believed that this movement was caused by space's actual expansion. Einstein's theory of a static universe was refuted in the 1990s by observations of supernova redshifts, which further demonstrated that the expansion was in fact speeding up. Ever since then, scientists have speculated on what might have caused the expansion, and many models and ideas have attempted to account for it. One scientist likened the finding to throwing a set of keys up in the air, expecting them to fall down, only to see them fly straight up toward the ceiling. It is now believed by scientists that quantum fluctuations in otherwise empty space provide a form of repulsive force that propels the universe's fast expansion. Furthermore, it appears that the force is becoming stronger as the cosmos expands. Most people think of dark energy as something that space has inherent characteristics with. When coupled with cold dark matter theory, it creates the most popular cosmological and astrophysical model of the universe, the lambda CDM model. The concept is based on the premise that vacuum energy, a kind of negative energy that pushes itself apart, is necessary for things in space to accelerate. The cosmological constant is used to express it, bringing back Einstein's biggest blunder, since it allows for a universe that is both dynamic and does not contradict the results of general relativity. By extrapolating from the expansion rate, we find that dark energy accounts for 68% of the total energy density in the universe. Nevertheless, according to models of quantum fields that explain vacuum energy, the cosmological constant would be around 100 times greater than it is now, necessitating an equally massive gravitational force to cancel it out. The lambda CDM model is still the most cost-effective explanation for dark energy and dark matter, even if other hypotheses are still being studied. Although several hypotheses have been proposed by scientists to explain the nature of dark matter and dark energy, none of them have been able to firmly integrate these theories with the physics and reality models that are in use today. Inevitably, this raises questions among scientists. Do dark energy and dark matter actually exist? Do we fully comprehend modern physics phenomena like quantum mechanics and gravity? Are these theories merely a means to an end, to the collapse of physics as we know it? In fact, scientists have looked at the possibility that our current knowledge of gravity might not be accurate. Modified Newtonian dynamics, or MOND, is a proposed model that tweaks Newtonian physics and general relativity in a way that makes them account for the effects of dark matter and dark energy. A number of theories, including this one, have recently emerged under the umbrella term modified gravity that aim to rethink fundamental ideas in the physical sciences. These hypotheses won over the public's trust when they filled in the gaps left by particle cold dark matter ideas, which failed to do so. For instance, MOND was able to account for low-surface brightness galaxies, or galaxies with a smaller stellar population but high levels of gravitational lensing, the bending of light passing near the galaxy, and was also able to predict star velocity curves more accurately than any other dark matter theory at the time. Then this must be the solution, right? Dark energy, and thus dark matter, are a joke, and all we have to do is reassess what we thought we knew, right? Not so fast. There are major problems with MOND and modified gravity as a whole. Firstly, it is not able to explain the universe's web-like structure. In fact, one of the few models that can explain it is cold dark matter. Furthermore, the distribution of heavy elements in the cosmos would be significantly larger if gravity operated differently from how we currently understand it. Due to these substantial differences, the majority of scientists now dismiss the idea of alternative gravity. The conclusion is obvious. Dark matter does exist. How will this play out in the years to come? There is undoubtedly more to be discovered in modern physics, and it may take us longer than our lifetimes to reach the completion of this endeavor. These are but a handful of the theories thrown out to try and solve the big mysteries surrounding dark energy and matter. Contrary to sensational headlines, we aren't even close to solving this mystery. Like most active study areas, science itself requires that all theories and information be subjected to constant testing and challenge. In the end, science is similar to the fabled Hydra, in that 10 new questions arise for every one that is answered. Modified gravity explanations, while they may add to the complexity of a given mystery, serve as a reminder of the value of the scientific process in carefully sorting out the facts from the murk that envelops all contemporary mysteries. Just as previous discoveries have utterly transformed the field of science, each new one possesses the capacity to do the same. Research is being conducted at a higher rate than in the past. The composition and structure of the universe, black holes, and gravity are now better understood than we could ever have imagined. You may be confident that the research will continue, and we can all wait anxiously to learn the mysteries of the deep universe. Let us know what you think in the comment section below. Don't forget to subscribe to our channel and put on notifications for more videos. See you soon.